In this lesson, we'll consider a physical application of an endpoint problem or boundary value problem. Suppose we have a tightly stretched, quickly spinning elastic string or rope of uniform linear density ρ, for example in kilograms per meter. Let us put this problem into the xy plane, and both x and y are in meters. The x-axis represents the position on the string. The string rotates at an angular velocity omega in radians per second. Imagine that the whole xy plane rotates at angular velocity omega. This way the string stays in this xy plane, and y measures its deflection from the equilibrium position y equals 0 on the x-axis. Hence the graph of y gives the shape of the string. We consider an ideal string with no volume, just a mathematical curve. We suppose the tension on the string is a constant T in newtons. Assuming that the deflection is small, we can use Newton's second law to get the equation T y double prime plus rho omega squared y equals 0. Let L be the length of the string in meters, and the string is fixed at the beginning and endpoints. Hence, y of 0 equals 0, and y of L equals 0, as pictured below. For the next step, we take the equation T y double prime plus rho omega squared y equals 0 and divide through by T, which gives us the equation y double prime plus rho omega squared divided by T times y equals 0. From here, the setup is similar to example 4.1.3, which we looked at earlier. I've copied this problem below. The only difference for this new problem is the interval length being L instead of pi. We are looking for the eigenvalues of y double prime plus lambda y equals 0, where y of 0 equals 0, and y of L equals 0, where now lambda is equal to rho omega squared divided by t. And since rho, omega, and t are all positive, there are no non-positive eigenvalues, and therefore we only have to consider lambda greater than 0. The general solution to the equation is y equals a cosine of square root lambda x plus b sine square root lambda x, and this is because the corresponding characteristic equation when lambda is greater than 0 is r squared plus lambda equals 0, where the roots are plus or minus I square root lambda, where the real part is 0, the imaginary part has a coefficient of square root lambda, giving us the general solution. And now we consider y of 0 equals 0, which implies that a equals 0. I've shown that work below in blue. If y of 0 equals 0, we have a cosine 0 plus b sine 0 equals 0, and because sine 0 is 0 and cosine 0 is 1, we know a must be 0. So if a is equal to 0, we now know y must equal b sine square root lambda x. And now we consider the condition y of L equals 0, which again I've shown here below in blue. If y of L is equal to 0, then we have the equation b sine of square root lambda L equals 0. This is true when b is 0, which we don't want, or when the sine function is 0. Recall the sine function is 0 when the input is a multiple of pi, which indicates the equation is true when square root lambda times L is equal to k times pi, where k is some integer greater than 0 or greater than or equal to 1. And if we solve this for lambda, we have lambda equals k squared pi squared divided by L squared, and recall that lambda is also equal to rho omega squared divided by t, which gives us the equation rho omega squared divided by t equals lambda, which equals k squared pi squared divided by L squared. So what does this say about the shape of the string? It says that for all parameters rho, omega, and t not satisfying the equation above, the string is in the equilibrium position y equals 0. When rho omega squared divided by t equals k squared pi squared divided by L squared, then the string will pop out some distance b, which remember is the coefficient of the sine function here. We cannot compute b with the information we have. And now let's assume that rho and t, which are the uniform linear density and the string tension, are fixed, and we are changing omega, the angular velocity. For most values of omega, the string is in the equilibrium position y equals 0. When the angular velocity omega hits a value of omega equals k pi times square root t divided by the product of L and the square root of rho, then the string pops out and has the shape of a sine wave crossing the x-axis k minus 1 times between the endpoints. This equation for omega came from solving the equation above for omega. And again, when omega hits this value, the string pops out and has the shape of a sine wave crossing the x-axis k minus 1 times between the endpoints. For example, at k equals 1, the string does not cross the x-axis, and the shape looks like figure 4.1, which is shown above. On the other hand, when k is equal to 3, the string crosses the x-axis 2 times, which is pictured below in figure 4.2. When omega changes again, the string returns to the equilibrium position. The higher the angular velocity, the more times it crosses the x-axis when it is popped out. For another example, if you have a spinning jump rope completely popped out, then k equals 1, and if you pull on the ends to increase the tension, then the velocity also increases for the rope to stay popped out. I hope you found this helpful.